Welcome to the new chapter of chemistry, that is classification of the elements and periodicity in the properties. Now in this chapter we are going to discuss about these topics, and our today's topic is genesis of the classification and modern periodic table. But before that, I want to ask you something. Whenever we put sodium in water, why it reacts violently with water? Why not iron? Sodium is metal, iron is also metal, but sodium is reacting violently, iron is not showing that characteristic. Why? Now you will say that sodium is very reactive, iron is less reactive, but how we will come to know that which element is reactive, which element is less reactive? So we need a classification for that these elements are reactive metals, these are less reactive metals, these are metalloids, and these are non-metals, right? And the classification of the elements started way back in 1817, and still in the continuation of that, in today's era, we study about the modern periodic table. Now, how did they construct this modern periodic table? They studied about the properties of the elements, and they kept the elements in the same place having the similar properties. And which properties they study about? The properties were atomic radius, ionization energy, electron affinity, electronegativity, and metallic character. One more thing I want to tell you, this chapter and the next chapter, that is chemical bonding and the molecular structure. The knowledge of both these chapters is the backbone of inorganic chemistry. And you are having chapters like S block, P block, DNF block. Knowledge of these two chapters will definitely help you to study those chapters easily. So let's start with the history of the classification of elements. So first was Dauvergne. In 1829, he gave some triplets, or you can say that Dauvergne triads. He gave the triplet of 3 elements. He said that the mass of the middle element will be equal to the arithmetic mean of first and the third element. So what he said, let's take the example. Suppose we have chlorine, bromine, and iodine. The atomic mass of the chlorine is 35.5. Atomic mass of the bromine is 80, and that of iodine is 127. Now first element is chlorine and the third element is 127. If we take the mean of this, means 35.5 plus 127 divided by 2, it comes out to be 81.25. It was near to that actual mass of bromine, that is equal to 80. Again we can take another example. Calcium, strontium, and barium, they have the atomic masses 40, 88, and 137. The first is 40, third is 137, and if we take the arithmetic mean of 40 and 137, that will be equal to 88.5. It is close to the mass of strontium. But this was not correct for all the elements. Then Newland came. Newland classified the elements on the basis of musical notes. Now if we talk about Hindi, we know that there are 7 musical notes like sa, re, ga, ma, pa, dha, ni, and again sa. So sa and sa are same. So he said that if this is sa, that is lithium, and this is sa, that is sodium, the properties, the chemical properties of lithium and sodium will be similar. And we can go further. Then sa, re, ga, ma, pa, dha, ni, and again sa. Sa means potassium. So lithium, sodium, potassium will have the similar properties. Although he was correct, but this was not correct after the calcium as transition element comes after this. So he did not know about transition element. That's why this table was correct up to here only. Then Mendeleev said that the properties of the elements are the periodic function of their atomic weights. What does it mean? It means that if we keep the elements in this table in increasing order of their mass, then the similar elements or the elements having the similar type of properties will fall in the same group. You can see clearly lithium, sodium, potassium, they are having the same properties and they are present in the same group, right? But there was some advantages, but there were some limitations also of this Mendeleev periodic table. Let's discuss those advantages. The first advantage was he classified the elements very well. So after the classification of the elements, what he did, he predicted the new elements also. He said that there will be an element below aluminium and silicon. He kept vacant space below aluminium and silicon, and he named the elements eka-aluminium and eka-silicon. Eka-aluminium became gallium and eka-silicon became germanium. And we all know that gallium has similar properties as aluminium and germanium has the similar properties as silicon. So that's how he predicted some new elements also. Now in the third point, he corrected some atomic masses with the help of the equivalent weight. So previously the atomic mass assigned to beryllium was 13.5 and he corrected the atomic mass of the beryllium and he said that its atomic mass should be equal to 9 AMU, and that was with the help of equivalent weight. Now, limitations. The first limitation was the position of hydrogen. We all know that hydrogen makes H plus ion and H minus ion also. So it has the properties similar to the alkali metals and that of halogens also. So there was not a certain place of hydrogen in the Mendeleev's periodic table. Now the next one is he kept some dissimilar elements in the same group. For example, you know that alkali metals are very reactive, but copper, silver, gold are very less reactive. But he kept those elements in the same group. That was wrong. So the third point is, he said that atomic mass will keep on increasing and the periodicity will generate, right? And the elements will come in the same group which are having the same properties. But somewhere in the table, you can see that atomic mass is decreasing also. Argon is having atomic mass 40. After that comes potassium. It is having less mass and that is 39 only. Cobalt 59 and after that nickel, that is 58.6 only. Tellurium 127.6 and iodine 127. So this was the anomaly in limitations of that Mendeleev periodic table. Now, there was no place for isotopes. We know that there are isotopes like carbon 12 and carbon 14. So carbon 12 was placed there. For carbon 14, there was no place. The last point is there was no place for noble gases. So we discussed about Daubernier, we discussed about Newlands, we discussed about Lothar-Meyer, we discussed about Mendeleev's periodic table. After that, modern periodic table came. Let's discuss about the modern periodic table. So guys, after the discussion of the history of classification of the elements, let's discuss about the modern periodic table. And the modern periodic table is based on a law, and that law is called Morden's periodic law. It states that the properties of the elements are the periodic functions of the atomic number. Now what does it mean? It means that when the atomic number increases, the same type of element will fall in the same group. Now what is this group? We have to understand the meaning of group and the periods. Let's take a look on the modern periodic table. So guys, here is the modern periodic table in front of you. Hydrogen is an element which does not have any place in the modern periodic table because its property matches with the alkali metals and the halogens also. So, before starting the setup of this modern periodic table, in which there are 18 vertical columns and 7 horizontal lines. These 7 horizontal lines are called periods and the vertical columns are called groups. Now my question is, why there are 18 groups? Why not 20 groups? Why not 16 groups? And why only 7 periods? Why not 6? And why not 8 periods? Let's discuss about this beautiful arrangement of the modern periodic table. So guys, first of all, the modern periodic table is divided into 4 parts. First, this is S block, and you can see that the electronic configuration of S block is NS122. It means that the electrons will be filled in the S subshell. Now one more thing I want to tell you. This modern periodic table, which is based on atomic number, actually it is based on the electronic configuration. So we have to follow FOU rule, right? So according to FOU rule, first we have to fill the S subshell. So in this case, the configuration is NS122, means we are filling the electrons in S subshell. That's why S block is called S block. Now, if we talk about the P block, the electronic configuration of P block is NS2 and NP126. The meaning is NS2 means we have already filled 2 electrons in the S subshell and now we will fill the electrons in P subshell. That is P1, P2, P3, P4, P5 and P6. That's why the P block is called P block. If you talk about the D block, then this electronic configuration you can see that it is D1 to 10, means we will fill the electrons from D1 to D10. And in F block, the filling of F subshell will take place. So if anybody asks you why S block is called S block, the simple answer is the filling of S subshells takes place. In P block, filling of P subshell takes place. In D block, filling of D subshell takes place. And in F block, filling of F subshell takes place. Right? Now let us talk about the periods first. There are 7 periods, but they does not have equal number of element. Why is it so? Let's talk about first period. In first period, there are hydrogen and helium. The electronic configuration is 1s1 and 1s2. And everybody know that in first shell, there is only one subshell and that is 1s. And in 1s, only 2 electrons can be filled. That's why there are 2 elements in first period. If we talk about the second period, it will start with lithium. The outer electronic configuration of lithium is 2s1, then it is beryllium 2s2. It means that S is filled and then it will come boron, carbon, nitrogen, oxygen, fluorine and neon. So 2 electrons in S subshell, 6 electrons in P subshell. 2 plus 6 is 8. That's why in the first period there are 2 elements, in the second period there are 8 elements. And if we talk about the third period, it follows the same sequence like second period, like 3s will be filled first and then 3p will be filled and the total number of elements will be 2 plus 6 again it is 8. If we talk about the fourth period, then 4s1, 4s2. After 4s2, there will be 3d. So the starting of filling of D subshell will take place. Means D1, D2, D3, and it will go up to D10. And then again P will start. P1, P2, P3, P4, P5 and P6. So how many electrons we have filled? 2 in the S subshell, 10 in the D subshell and 6 in the P subshell. So 2 plus 10 plus 6 is equal to 18. Now same for the fifth period. Again 2 plus 10 plus 6, that is equal to 18. So that's why it is like 2, 8, 8, 18, 18. Now the period number 6. Now we'll start with 6s1, then 6s2, then 5d1. Now this is lanthanum. Now here the lanthanoids start, and we don't have any place to keep these lanthanoid series in the periodic table. That's why they are given here down in the F block. So it will start with cerium having the atomic number 58 and it will end up to lutetium. There will be 14 elements in the lanthanoids. It means that in the sixth period and third group, there will be 15 elements in total. But as we don't have space to write them, that's why only we write lanthanum over there, and all 14 other elements are written in the F block. Then D will start. After that we will fill P subshell, and if we talk about the total number of elements, the subshells which we have filled are S, P, D and F. So 2 electrons in S subshell, 6 electrons in P subshell, 10 electrons in D subshell and 14 electrons in F subshell. So the total is 2 plus 6 plus 10 plus 14, that is equal to 32. It means that the sixth period is the longest period in the modern periodic table. So this is the story of periods. Let's talk about some important groups. Now group number 1. Now these elements are called alkali metals: lithium, sodium, potassium, rubidium, cesium. Because on dissolving in water, they form strong bases like NaOH and KOH. If we talk about the second group, beryllium, magnesium, calcium, strontium and barium, they does not found in nature in the native state. But we can found their oxide which are very alkaline in the earth crust. That's why they are called alkaline earth metals. If we talk about the 18th group, the group number 18 is called noble gases. The elements are called noble gases or inert gases because they does not react with any other element. But you will study that xenon can form the fluorides also and oxide also, right? If we talk about the group number 17, this is called halogen. Halo means salt and gen means generator. It means that they are salt producers. So we know that the salts are fluoride, chloride, bromide and iodide. The next group is group number 16, that is chalcogens. Chalco means ore, gen means generator. The meaning is ore producer. And there are generally either oxide ores or sulfide ores, and oxygen and sulfur both are present in this group. The group number 15, the elements are called pnictogens. Pnicto means the suffocation. So they form the gases or the compounds which cause the suffocation. That's why they are called pnictogens. Now, if we talk about the transition elements, Now many of the student thinks that the D block is transition element. They are transition element. The actual definition of the transition element is the incomplete D subshell. So the element which have incomplete D subshell, that will be the transition element, and it means that zinc, cadmium and mercury are not transition elements, right? If we talk about the group number 11, copper, silver, gold, this is called coinage metals. So these are coinage metal, means we can make coins of these elements, right? And one more thing I want to tell you, in case of alkaline earth metals, that beryllium, that is not considered as alkaline earth metal because BeO, its oxide is amphoteric. That you have to keep in mind, right guys? So this was whole about the Morden's periodic table. Let's look at the limitations of the Morden's periodic table. The first limitation is the position of hydrogen is still not fixed in the Morden's periodic table, and the position of lanthanoids and actinoids is also not fixed. So this was whole about the Morden's periodic table we follow. Now let's move on to the nomenclature of those elements which have atomic number more than